So today in this class I am going to have a talk for the nonlinear optics. Now let's start the topic with linear optics and nonlinear optics. That is the difference between the linear optics and the nonlinear optics. As we know that the dielectric or the medium polarization, material polarization, if it is expressed as P, then P equals to chi into E, where chi is the susceptibility, dielectric susceptibility, and capital E is the electric field of the material. Now in this equation, as you can see that this equation number 1 is a linear equation. It is a linear equation as because that capital P is directly proportional to the electric field intensity or capital E. As also we know that the refractive index of a material is also dependent on the dielectric susceptibility. So if for any case that the polarization vector capital P does not depend on the electric field intensity, that is capital E, so thus the refractive index of the medium will also not dependent on the intensity of the electric field. So here I am talking about two different things. As this equation number 1 is a valid equation, that is the polarization of a material or the medium polarization is directly proportional to the electric field, where chi is the dielectric susceptibility, and as we know that refractive index of a medium or refractive index of a material is also a function of the dielectric susceptibility chi. Now if for any substance, if the polarization does not depend on capital E, then also that refractive index is also independent of the dielectric susceptibility as a whole. And in this part I am actually talking about the linear optics era. So before the invention of the laser, this was the facts that any material or the refractive index of any material is actually linearly dependent on the electric field or capital E. So thus the dielectric polarization capital P is also a function of the electric field E. Now after the invention of laser, that is after the year 1960, when the laser was invented, the situation, that is the respective field intensity capital E is actually raised off to the order of 10 to the power 8 to 10 to the power 10 volts per centimeter, and that becomes actually comparable with that acting on the domain of the atoms in the metal. So after the invention of laser, that is after the year 1960, laser means a high intense electric field or a high intense optical source, as we know, and the order of the intensity is 10 to the power 8 to 10 to the power 10 volts per centimeter. And this amount of electric field intensity or this amount of intensity is actually comparable to the domain of the atoms in the metal. And thus the field intensity of such a highly intense beam, it become comparable or it become capable of changing the dielectric polarization of the material, and so thus the dielectric susceptibility become affected by the electric beam of light intensity. So what I am talking about, that after the invention of laser, that is beyond the year 1960, when laser becomes popular, then the electric intensity or field intensity of laser, as we know that laser is a highly intense electric field, and the electric field intensity, it is actually of the order of 10 to the power 8 to 10 to the power 10 volts per centimeter. Now what it does, it actually it can change the atomic dimension, or it can be comparable of the domain of the atoms in the material, and hence for such a high intense electric field or high intense beam, the field intensity, as because the laser has got a high intense field intensity, it becomes capable of changing the dielectric polarization of the material. So the dielectric polarization, which is actually is a function of capital E, and thus if the electric field intensity of the laser becomes very high, so that means the dielectric polarization is now effective or is now affected by the large value of electric field intensity of the laser beam itself. And hence the dielectric susceptibility, that is chi, become affected by the electric beam of light intensity. So it can be said that in such a case, that is when in place of an ordinary light beam, if an intense laser beam is used, the dielectric susceptibility behaves as a function of the electric field. So the dielectric susceptibility, that is chi, can be written as a function of this highly intense electric field. That is, chi becomes a function of capital E, and it can be written as chi 0 plus chi 1 E plus chi 2 E squared, and so on. Right? Is it okay? So now in terms of equation 2, equation 1 also can be written as P equals to, so now P, which is also a function of capital E, it can be written as, we can substitute equation 2 in equation 1, and we have chi 0 E plus chi 1 E square plus chi 2 E cube, and so on. Okay? So this is our equation number 3. Any problem up to this? So now from equation 3, what we can conclude? We can conclude that the dielectric polarization capital P is now no longer linear. If we compare equation 1 or equation 3, that is equation 3 with equation 1, in equation 1 what we have found, that P is a linear equation with E. Now after putting the value of chi from equation 2 in equation 1, we have equation number 3, and this equation tells us that now the dielectric polarization capital P is no longer a linear equation of capital E, but it becomes a non-linear relationship with capital E. Right? So this is the non-linearity of an optical medium. So now we have come to a point where the non-linearity of any optical medium appears, and this is nothing but due to the fact of the highly intense electric field intensity, which is a characteristic of the laser beam itself. Okay. So now from equation 3, now if we if we give a look at equation number 3, what we have found? We can found that here first term is chi 0 e. This is actually nothing but it is actually the linear relationship holds here chi 0 e. So this equation number 1 we can write it as the linear polarization term PL, linear polarization term, that is chi 0 e. So the first term can be written as the linear polarization PL, and then the second term, that is chi 1 e square, can be written as nonlinear PNL1. So that is the nonlinear first order nonlinear term. Then the second term can be written as PNL2, that is the second term. Chi 2 e cube can be written as PNL2, and so on and so on. Okay. So the first term is PL, and that is chi 0 e. Let it be equation number. Now if this can be written as equation 4, then this is equation number 5, where the linear term, linear polarization PL, is written as chi 0 e. So this is actually the linear polarization term, and due to the presence of this term, all the effect as it was seen for linear optics will also be observed in case of non-linear optics. So keep it in your mind that whenever we are talking about non-linear optics, it means that this presence of this linear term, every time when we are talking about the non-linear optics, this linear term is also present there. So the linear optical effects, what we have found already in our previous physics discussions, will all be actually present in the non-linear optical domain. So it is not the fact that when we are talking about the non-linear optics, those linear optical phenomena, that is interference, diffraction, polarization, and so on, they are not present in the non-linear domain. They are present in the non-linear optics as well because of the term PL, that is the linear term is also present there. So when we are talking about non-linear optics, linear effects are present as well as some non-linear effects are also present, and these two actually make the non-linear optics. Okay. Sorry. So now let us talk about the second term of equation 4, that is PNL1. So let us talk about the second term PNL1 of equation 4, and it is chi 1 e square. So it is chi 1 e square. Let it be equation number 6. Now this is the first order. This is the first order non-linearity. This is the first order non-linearity shown in case of the interaction of an intense polarized laser beam with an optical dielectric material. Here chi 1 is the first order non-linear susceptibility term. You can't see the board, Shutyajit. কেউই কি বুঝতে পারছো না বোর্ডের লেখা? Is it not visible to you all? Okay. Okay, fine. Okay. Then I continue. Fine. Thank you. So now let's talk about the next term, that is the third term, and it is also a non-linear term, and it is the second order non-linear term PNL2, and it is given as PNL2, and it is given as chi2 E cube. So let it be equation 7, and here also we can find that this can be represented as the second order nonlinear polarization term, and again here chi2 is the second order nonlinear susceptibility term. So chi1 is the first order nonlinear susceptibility term, chi2 is the second order nonlinear susceptibility term. Fine. So now what happens when a high power laser interacts with an optical dielectric material? So what happens? Now we are actually considering the fact that we have a highly powerful laser which is going to interact with an optical dielectric material, and we can talk about three effects. We can talk about three effects which can be observed for this interaction, or rather after this interaction, and these are firstly the linear effect. So three effects can be understood from these three components or from these three equations 5, 6 and 7. So when a highly powerful laser beam interacts with these dielectric material, three things can be observed. Number one, the linear effect due to the term PL. So this is the linear effect. Then proceeding towards equation number 6, the second effect can be observed as the first order non-linear effect, and thereafter the second order non-linear effect. So three things can be observed. Firstly, the linear effect due to equation number 5. Secondly, the non-linear or the first order non-linear effect due to equation number 6. And thirdly, due to equation number 7, the second order non-linear effect. So whenever a highly intense laser beam interacts with a dielectric material, three observations can be there. Number one, the linear, and number two, the first order non-linear effect, and lastly or thirdly, the second order non-linear effects. Okay? Now, there are few materials in which the second order effect is strong. আরে বেলটা বাজাচ্ছে কে দেখো? So there are few materials where the second order effect is strong. That is, chi2 is considerably high. So in our treatment we will give special effort on the linear term and on the first order non-linear effect of the material with the application of laser. So in our treatment we will give special effort on the linear term and on the first order nonlinear effect of the material with the application of laser. So what I am talking about, that there are few materials only in which we can find that the second order nonlinear term is dominant or is strong. That is, chi2 is considerably high. Now in our treatment we will give special effort on the linear term and on the first order nonlinear effective of the material with the application of laser. So therefore, for our study for such materials, that capital P or dielectric polarization can be written as only the linear polarization term, that is PL, and plus the first order nonlinear term, that is PNL1. So now we are not bothered about the second order nonlinear term PNL2. Is it right? Is it okay? So now we are going to consider our discussions. For our discussions, capital P can be written as PL plus PNL1. So we actually omit the second order nonlinear effects, where PL is, as we already know, that PL is chi0 E and PNL1 equals to chi1 E square. Fine? If you have any questions, please ask me. Okay? Okay. So, so now up to this, what we have found, that now we have a non-linear material, or rather we have a medium, a material which has a non-linear effect as well as it has the linear effect. We have excluded the second order or the higher order nonlinear effects. So after this, we have all our discussions. Is it okay? Am I audible? Fine. So now we have arrived at this point of our class, of our lecture, in which we have a material, an optical medium or an optical material, in which we are going to incident a highly intense laser beam, and we are going to observe the effects, and these effects are nothing but there will be two effects. I have earlier discussed that there will be three effects. Number one, the linear; number two, the first order nonlinear; and number three, the second order nonlinear. But now I am actually confined our discussion within a space in which the linear effect and the first order nonlinear effects are present. Okay? Normally, all dielectric materials have some non-linear effects when they actually interact with such a polarized intense laser beam. But we do not call all such material as non-linear material. Why? So every time if you go across or if you find a dielectric material, and if you are interested to find out the interaction of a highly intense laser beam with that particular dielectric material, you will find that there are some non-linearity presence there. But this doesn't mean that all dielectric materials can be regarded as non-linear materials, right? So some of the materials are regarded only non-linear materials, but all the dielectric materials, those of which all exhibit some non-linear effects, they are not regarded as non-linear materials. Why? As because if materials which are non-linear, the materials which are regarded as non-linear materials, where chi1, the value of the first order non-linear susceptibility, that is chi1 present in equation number 6. If for a material the value of chi1, that is the first order non-linear susceptibility, is very high, so after the application of a reasonable electric field, this value chi1 e square becomes comparable or rather becomes significant in comparison to chi0 e. So what I am talking about, that every time if you find any dielectric material, you will observe that if a highly intense, highly polarized optical beam such as a laser is interacted with that particular dielectric material, you will always find some non-linear effects there. But that doesn't mean that every non-linear material or every dielectric material is a non-linear material. That is not the case. But some of the materials are regarded, that is, some of the dielectric materials are regarded as non-linear material, as because if there the value of chi1, that is the first order non-linear susceptibility term, is high enough so that with a reasonable electric field intensity or with a reasonable intense optical beam, if the value of chi1 e square is significant in comparison with chi0 e, then only those materials, those dielectric materials are known as or are regarded as the non-linear materials. Okay, so every time whenever you find a dielectric material, don't go for it as a non-linear material. Some of the dielectric materials, example such as KDP. KDP means potassium dihydrogen phosphate, ammonium dihydrogen phosphate, that is another example. ADP, CDA, lithium niobate, lithium cesium dihydrogen. These are some of the examples of non-linear materials. So potassium dihydrogen phosphate, that is KDP, this is an example of a non-linear material. ADP, that is ammonium dihydrogen phosphate, ADP, this is also an example. Lithium niobate, that is LiNbO3. So these are some examples of non-linear material. That means in such materials the value of chi1 is very high, and for this reason whenever a reasonable value of electric field intensity light beam interacts with this material, the value of chi1 E square is significant with comparison to chi0 E. So this is the essence, this is the significance of whenever why a non-linear, why a dielectric can be regarded as a non-linear material. Is it okay? Have you understood? Is it okay? If you have any question, go forward. So in a nutshell, what we have already discussed, we have discussed about the linear optics, or rather the difference between the linear optics and the non-linear optics, and why some materials can be regarded as non-linear materials. So now we have our discussion, or we are heading towards this to discuss interaction of laser with a nonlinear material which has a first order nonlinearity. So now we are going to discuss about the interaction of a laser beam with a dielectric material or with a nonlinear material which has a first order nonlinearity. So the examples are KDP, ADP, lithium niobate, LiNbO3, lithium niobate, LiNbO3. These are the examples of some non-linear materials. So now let's discuss about the interaction of laser with a dielectric material which has a first order nonlinearity. So for this to discuss, we consider a plane polarized monochromatic light wave of frequency f traveling at velocity v, or rather v1, in the nonlinear material. So the electric field strength, we can write it as E1 ZT, and it can be written as E01, where E01 is the intensity, cos 2 pi f into T minus Z by V1. So let it be equation number, the last equation was equation 7, so this is equation number 8. So this is a plane polarized monochromatic light wave which has a frequency f which is traveling along the axis z with a velocity v1 within the nonlinear material. Here E01 is the amplitude of the wave. So here this is the nonlinear material, and the wave is traveling, that is E1zt. This wave is traveling inside the nonlinear material, and where we have two dielectric susceptibilities. One is chi0, that is the linear susceptibility term, and the other is chi1. So these two are present here, and this is actually the z axis, the z direction. So now substituting the value of E in equation 6. In equation 6 was our PNL1. Now we have only considering the first order non-linearity. So there will be no point to mention NL1, NL2. So this is nothing but only PNL, and PNL was chi1 and then E square. Now here in equation 8 we have the value of E1. So putting the value of E1 here, or E1 square here, we have E01 square and then cos square 2 pi f into t minus of z by v1. So this is equation number 9. Okay. So we have substituted the value as given in equation 8 in equation number 6. So the equation number 8 is written as E1zt equals to E01 cos 2 pi f into t minus z by v1. That is equation number 8. And we have substituted equation number 8 in equation number 6, in which equation number 6 was PNL1 equals to chi1 E square, but as I have mentioned that now we are considering only the first order nonlinear effect, so there is no point to mention NL1, NL2, so I have written as PNL, and that equals to chi1 into E square, and in the part of E square I have substituted the value of equation number 8 here, and we have chi1 E01 square cos square then 2 pi f into t minus of z by v1, and that is equation number 9, right? Now let's proceed further, and here we can have we can write this equation as half of chi1 E01 square and then twice cos square 2 pi f into t minus of z by v1. We can write it as because now I am going to expand this 2 cos square theta, and it will be 1 plus cos 2 theta. So 1 plus cos 2 theta, and then we have half of chi1 E01 square, that is 1 plus cos 2 theta, that means half chi1 E01 square, then cos 2 theta, that means 4 pi f into t minus of z by v1. Is it okay? This will be our equation number 10, right? Is it okay? So up to this, that is, we have the nonlinear term PNL, and that is actually half chi1 E01 square plus half chi1 E01 square, then cos 4 pi f into t minus z by v1. Right? Now we have the linear effect also. Remember that linear term? So now we are going to find out the linear effect also, and that was PL, that is the linear part, and it was chi 0 E. So just put the value of E here and it will be chi 0 then E01 cos of 2 pi f and then t minus of z by v1. So this is the linear effect, or this is the linear term. This is the linear term which is also present inside the non-linear material. So these are the two effects, these are the two mathematical relations, or these are the two effects will be present whenever this electric field intensity or the light what we have taken here is incident on the non-linear material which has two dielectric susceptibilities. One is the linear susceptibility term chi 0 and the other one is the first order non-linear susceptibility term chi 1. So due to the presence of these two non-linear dielectric susceptibility terms, we have these two equations. One is the linear effect, or we have calculated the linear effect in equation number 11, and in equation number 10 we have already calculated the first order or the non-linear effect PNL, right? So we can conclude that if we send an intense laser beam through a non-linear material, we should get these following or these electric fields according to equation number 10 and 11. Now let us consider the terms independently what we have found in these two equations, that is in equation 10 as well as in equation 11. Now the first term in equation 10 what we have found is this, half chi 1 E01 square, half chi 1 E01 square, and this term you can regard it as a DC field, a DC value, as because chi 1 is the first order dielectric non-linear dielectric susceptibility term, and E01 is the amplitude of the electric field intensity. So this is actually a DC field. This is actually a DC field. Is it okay? Have you any problem? Dolly, is it okay? Just give me a thumbs up if it is okay. 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 So we have we have one term from these two equations. We have found that first term, or one of the term is half chi 1 E01 square. It is basically a DC field. It is basically a DC field, as because all the terms are constant, so it is a DC field. Now secondly, the second term what appears here is this, that is half chi 1 E01 square cos 4 pi f into t minus of z by v1. This is the second term. This is the second term. And as you can find that this can be written as a secondary light wave if we express it as that E2 equals to, now this half chi1 E01 square, if we replace it by E02, this is the amplitude E02, so it can be written as E02 cos 2 pi into 2f, that makes that 4 pi f, and then t minus of z by v2, and let it be equation number 12. So just focus on this second term, and the second term is half chi1 E01 square cos 4 pi f t minus z by v1, and this equation can be written as, if we replace this half chi1 E01 square as E02, and if we regard it as, because it represents a wave, a field, as because this is not the constants here, as we have find it here, half of chi1 E01 square, all of the terms are constant, as because chi1 is the susceptibility, first order nonlinear susceptibility term, E01 is the amplitude of the wave, so these all are constants in the first term, but in the second term, as cos function is presented here, so we can regard this as a secondary wave, and then we can write it as 4 pi f can be regarded as 2 pi into 2f. So remember that when we have taken the original wave, we have taken it as a wave which has a frequency f, which is propagating along the z-axis with a velocity v1, but as because the frequency is changed here, we actually write it as 2 pi into not f but 2 pi into 2f, so the velocity v1 is also changed and we have written it as v2. Okay, so we have came across a second wave or a secondary wave, secondary light wave, and this can be represented by equation number 12. So the wave has got a frequency of twice f, and the secondary wave has a velocity of v2. Now let's find out the last value, that is number 3. Here also you can see that this is also represented, this is also a wave. This also represents another wave, but this time the frequency is not changed. The frequency remains the same as the incident frequency, or as the frequency of the incident wave, that is f. So here we have find out just the amplitude has been changed, and the amplitude becomes chi0 E01. So here another wave has also been formed, but with the same frequency f, but with a different amplitude, that is chi0 E01. So we have, after the interaction of an intense highly polarized laser beam with a first order nonlinear material, we have three fields present. Number one is a DC field. Number two, a secondary wave with a frequency of twice f of the, or twice the frequency of the incident wave. And number three, another wave which has got the same frequency of the incident wave. Is it clear? And the secondary wave, which I have talked here, which has got the double the frequency of the incident wave, that is twice of f. This particular wave, this particular secondary wave is called the second harmonic wave. This is the second harmonic wave, and this type of nonlinear material may produce second harmonic generation of light. So particularly after the interaction of the highly intense laser beam with a nonlinear, or rather with a first order nonlinear dielectric material, we came across a secondary wave. We came across a second harmonic generated wave, and this wave, why it is called the second harmonic, as because the frequency of this secondary wave is just double the frequency of the incident wave. Why is the velocity changed? As because I think you just type the question without having thinking about the question or the answer, as because a frequency of a wave is changed, whether the velocity is a constant value. So as because the frequency of the wave is changed, we must represent it as another velocity value, and that is v2. As the frequency has been changed, the frequency was initially f, and now the frequency has written as twice f, so we must change the velocity v1 to v2. Right, Abhijit? As because this velocity is the velocity of the wave inside the material, inside the dielectric material or inside the nonlinear material. So as because the frequency of the wave is changed, so the velocity must change itself. Fine. Okay. So we have came across that a secondary second harmonic wave can be generated. Now okay. So how this second harmonic wave is generated inside a laboratory? Now inside a laboratory, inside the lab, what we have to do, first of all, we have to take a first order nonlinear material, as I have already discussed. That is, it may be KDP, it may be ADP, it may be lithium niobate. Just take this type of materials. So this is the nonlinear material, and let it be the light of frequency f. So this is the incident light. This is the incident light, and with this arrow, you know that this arrow I am talking about the polarization state or state of polarization of the light. So this is the nonlinear material, and this is the optical axis. So this angle is theta. Now after passing within this nonlinear material, what happened? We find that we have one component as the secondary wave or the second harmonic wave. So if the polarization is this, so actually by putting the dot itself, what I am trying to convey, that this polarization or the state of polarization is actually perpendicular to the state of polarization given here, and this is the light of twice f frequency, this is the light of frequency twice f, and thereafter the original wave or another wave that is having the same frequency f is also found, and this is in this wave or the state of polarization of this wave is actually similar to the state of polarization of the incident wave, and this is the light of frequency f. Light of frequency f. So this is how the second harmonic generation takes place. So here in this figure I am actually show a schematic diagram of the whole process, which is known as the second harmonic generation. Here the plane of polarization, as we know of ordinary wave and that of the extraordinary wave, are mutually perpendicular. So if the input wave of frequency f has the polarization state perpendicular to the plane of the paper, here to the plane of the board, then its second harmonic wave, that is the light of frequency twice f, must carry its polarization state to the plane of the paper. If this is the perpendicular to the plane of the paper, this polarization state is to the plane of the paper. And here here what I have talking about, I am talking about the second harmonic generation and inside a laboratory. So to make a second harmonic wave, we must consider a highly intense optical source or highly intense light beam, which must interact with the uniaxial crystal or with the uniaxial crystal of the non-linear material, and after that we have two components. One is the second harmonic wave and the other one is the secondary wave, which is actually has the same frequency but with a different amplitude in compared with the incident beam. Okay. Now to make this happen, you have to, or we have to comply with the another condition, and what is known as the phase matching condition. So now this is also a very important topic to discuss here, that is the phase matching condition. So now we are considering that we are going to generate a second harmonic wave from a single frequency wave. So we have a wave of frequency f, and we are interested to generate a wave which has double the frequency of the incident wave. So to make it happen, this was the schematic diagram what I have shown here. And now this particular condition, that is the phase matching condition, is going to be a very vital part of this generation, because the phase matching condition is nothing but it can be represented as the momentum conservation principle. It is nothing but actually the momentum conservation principle, that is the phase matching condition. Therefore, for the transition from a plain monochromatic wave to its second harmonic counterpart, the phase matching condition or the momentum conservation principle must hold. What we are talking about, that we have taken a wave, a plain monochromatic wave of frequency f, and after passes through the nonlinear material, a second harmonic wave is generated. So actually, for the transfer of this f frequency wave to the twice f frequency wave, actually the conservation principle or the momentum conservation should be taken place, and this is nothing but the phase matching condition. So what we have already discussed, that we have seen that if v1 is the velocity of the input light having a frequency f, and v2 is the velocity of the second harmonic wave having the frequency twice f. So the momentum of input light, if the momentum of input light is k1, if the momentum of the input light is k1 and the momentum of the second harmonic wave is k2, now to hold the momentum conservation, that k1 must be equals to k2, right? So to hold the momentum conservation, if k1 is the momentum of the incident light wave and k2 is the momentum of the secondary wave or the second harmonic wave, and to have the momentum conservation intact, we must have k1 equals to k2. Now, if the direction of input light and that of the second harmonic light lies in the same direction, we can write this equation. I think this should be written as equation number 13. So, if the input light, that is the momentum, if the input light, that is the direction of the input light and the second harmonic wave have in the same direction, then we can write it equation 13 as k1, that is we can write the scalar values of k1 must be equals to k2, and this is equation 14. Now from classical mechanics, to hold momentum conservation, we know that mv1 must be equals to mv2. So that means v1 must be equals to v2 to hold. So where m is the mass of the moving photon of both input and the second harmonic wave. Okay? So equation 15, from equation 15 we can write v1 as v1 can be written as c by the refractive index, that is nf, and if v2 can be written as c by n but with different frequency twice f, that means from equation 15 we actually have c by nf is equals to c by n with 2f, and then cc cancels, that means n of f must be equals to n of twice f, and this is actually the phase matching condition. Equation number 17, c by nf equals to c by n2f. If it is equation 16, then this equation is equation 17, where this is the phase matching condition, and the significance of this, that is the phase matching condition, means that the refractive indices of the input light wave, refractive indices of the input light wave, that is n of f, is equals to the refractive index or refractive indices of the second harmonic waves. So if the incident wave and the second harmonic wave, or if the refractive indices of the incident wave and the second harmonic wave are equal, then the phase matching condition is satisfied, and we have the second harmonic wave inside the non-linear material. So to have a second harmonic wave, we have to maintain this equation, we have to follow this equation, or we have to follow the phase matching condition, as it tells that the refractive index of the incident wave becomes equal to the refractive index of the second harmonic wave, then only the phase matching condition is satisfied and we have the second harmonic wave inside a non-linear material. Is it okay? Is it okay? Any queries, any questions? Now, the last part of this discussion. So, we have to maintain the values of the refractive indices. We have to make the refractive indices of the incident as well as the second harmonic wave equal. Now, in the schematic diagram also what we have found? We found that whenever an incident light is entered into the non-linear material or into the crystal, that is an anisotropic crystal, and in an anisotropic crystal the refractive index actually depends on the direction in the anisotropic crystal. So whenever a light wave entered in this type of crystals, it actually splits. It actually splits into two, and the first one is the ordinary ray and the other one is the extraordinary ray. So one is the ordinary wave and the other is the extraordinary wave. A light wave when entered into the anisotropic crystal, it actually splits into two waves, and these waves travel at different velocities. Now, in many anisotropic materials, one of the light wave, that is the which we are talking about, the ordinary wave, it shows its refractive index independent of the direction of propagation, whereas the other one, that is the extraordinary wave, shows its refractive index dependent on the direction of propagation, and this type of crystal is known as the uniaxial crystal. So actually, to make happen or to make this second harmonic wave generation of second harmonic wave, these type of uniaxial crystals are taken, and the inside a uniaxial crystal, whenever a light enters, it actually splits into two. One is the ordinary wave, in which the refractive index actually does not change with the direction of propagation, and the other one is the extraordinary ray, in which the refractive index varies. It changes with the direction of propagation of the light. Now here I am going to draw two figures. One is one showing the refractive index variation of ordinary wave, and the other is the refractive index variation of the extraordinary wave with direction. Now the surface for the ordinary light is a sphere, and that of the extraordinary light is an ellipsoid. So this is the surface of the refractive index variation, or this is the refractive index variation for the ordinary ray. Let this be the optical crystal. Okay, so this is the optic axis. This is the optic axis, and this one is a sphere. Which actually shows the refractive index variation of ordinary wave. And for the extraordinary wave, this is the ellipsoid pattern, and it actually shows the refractive index variation for the extraordinary wave. So this is the refractive index of O wave, ordinary wave, and this one, this ellipsoid, is the variation of refractive index of E wave. Okay, have you got it? So this is the refractive index variation of the ordinary wave, and the ellipsoid shows the refractive index variation of the extraordinary wave, and you can see from these two surfaces that the refractive index of the ordinary wave, as it is a sphere, it actually remains the same in which direction you are propagating. It doesn't depend. But for the ellipsoid, the refractive index actually changes. It changes for the direction of propagation. Okay? Now to make the phase matching condition. So now we are going to hold the phase matching condition, and what we have already discussed, that for the phase matching condition, the frequency, the refractive index NF must be equals to N2F, right? So this was the phase matching condition. Now to hold the phase matching condition, actually now whenever the secondary wave is generated, what happens, that the light enters into the crystal, splits into two, one is the ordinary, other one is the extraordinary, and these two waves having the same frequency of F. Now after passing the non-linear material, when it emerges outside the material, we have the secondary wave. Now this secondary wave also has two components. One is for the ordinary wave and the other is for the extraordinary wave. So now consider there are four components. Two is ordinary wave, two are the extraordinary wave. Within two ordinary wave, we have one wave with a frequency F, one is the frequency of 2F, and as well as for the extraordinary wave, we have also one with a frequency F and the other is with the frequency 2F, right? So now I am going to draw the refractive index variations of all these four components inside this one picture, inside this one figure, right? So now if I am considering that refractive index of ordinary wave with the first sphere, the first ellipse of refractive index of extraordinary wave. Now if these are the refractive index variations, there are refractive index of ordinary wave with frequency F. This one is the F wave, and refractive index of E wave with again frequency F. So if these are the F frequency waves, then the refractive index variation of the 2F wave will be larger than this. The sphere should be larger than this. I think it will be harder for me. So let these components are for 2F. So now I am going to draw refractive index variation of F wave. And for this, I am going to draw it with these dotted lines. So this dotted line, this one is the refractive index of ordinary wave for twice F frequency, of F frequency. So the dotted line depicts here the refractive index variation for the ordinary wave but with the frequency F. And now this is the ellipsoid, and this will be the refractive index variation of extraordinary wave for frequency F. So I have drawn four components inside one figure. The outside sphere is the refractive index of ordinary wave with twice F. The inside dotted sphere represents the refractive index of the ordinary wave with frequency F. Now the outside ellipsoid is the refractive index of E wave with a frequency twice f, and the inside ellipsoid gives the refractive index variation of extraordinary wave with a frequency f. Okay? Now what happens to the phase matching condition? As you can see that we have in the phase matching condition, we have actually, if the phase matching condition is rewritten, let us consider these points and give a dot here. Now these 4 points, just consider these 4 points, and I am going to connect this. I am going to connect this one, extending it. So these 4 points, let they be A, B, C and D. A, B, C and D. Now these are the angles theta. Now in these points, just consider these 4 points A, B, C, D. These actual points, these 4 points were the index ellipsoid for the extraordinary wave of frequency twice f. Consider just only the point A. This will be the same for all the 4 points. Consider the point A. Here what we have find, the index ellipsoid, that is the larger ellipsoid which has a frequency of twice f, it actually intersects with the dotted line, with the dotted sphere, that is the refractive index of O wave for frequency f. So for these 4 points, that is for A, B, C and D, what we have found? We found that is the refractive index of ordinary wave having a frequency f. Ordinary wave having a frequency f, that is the dotted sphere inside, actually equals to the refractive index of the extraordinary wave having frequency twice f, that is the larger ellipsoid here. So what we have discussed just before in the phase matching condition, that is we must have NF equals to N2F, that remains the same here, that actually satisfies. So if a light is incident, and we have used the direction OA, OB, let it be O. So if we incident the light inside the crystal having direction, with making a direction OA, OB, OC or OD, we can see that in these directions actually NOF, that is the refractive index of the ordinary wave having frequency f, is actually equals to the extra refractive index of the extraordinary wave having a frequency twice f. So in a nutshell, we can say that in a nonlinear uniaxial anisotropic crystal, if a plane monochromatic wave of sufficient intensity is sent in those specific direction as an ordinary wave, then in the same direction it is possible to generate a second harmonic wave which has a frequency twice the value of the incident wave. So in this particular lecture, I have discussed about the nonlinear effect, the nonlinear materials, then the mathematical derivation of second harmonic generation. After that, I have discussed about inside a laboratory how we can develop a second harmonic wave. Then we have discussed about the phase matching condition, and later on, lastly, we have discussed how this phase matching condition is satisfied inside a crystal whenever we are going to generate a second harmonic wave. Last point that I want to discuss with you, that if I want to generate a higher harmonic wave beyond the twice f component. So now, just from analogy, we can tell that what happened, we have taken a wave of frequency f. After passing through the nonlinear uniaxial anisotropic crystal, we have found the wave of 2f frequency. Now, if the 2f frequency wave has sufficient energy, or rather has a sufficient value of electric field intensity, if this particular wave, which has a frequency of twice f, is now passing through another anisotropic uniaxial nonlinear crystal, what happened? Then we must find another wave of frequency 4f, as because again the second harmonic wave is going to generate. So in a whole, we have taken a wave of frequency f. After firstly passing through a nonlinear material, we have found a twice f component. Then after that, then this particular component, that is the second harmonic wave, if it passes through another uniaxial crystal and if it has got a sufficient amount of intensity, then again a second harmonic wave must generate, that is, a wave must be generated having a frequency of 4f. So in a whole, we can generate a twice f, that is the second harmonic wave, the fourth harmonic wave, and so on. So this is the entire discussion of your first part of the syllabus, that is the about non-linear optics. I think you all find it useful. So goodbye.